Hello and welcome to ASteMR. In this video we're going to take a look at this book, An Introduction to Radio Frequency Engineering by Christopher Coleman. We're just going to read a little bit into the book, see how far we get, and if hopefully you find it relaxing and informative. So, this book provides a comprehensive introduction to radio frequency, RF engineering, using a straightforward and easy to understand approach, combined with numerous world examples, illustrations and homework problems. The author has focused on minimizing the mathematics needed to grasp the subject while providing a solid theoretical foundation for the students. Emphasis is also placed on the practical aspects of radio engineering. The book provides a broad coverage of RF systems, circuit design, antennas, propagation, and digital techniques. Written for upper-level undergraduate courses, it will also provide an excellent introduction to the subject for graduate students, researchers, and practicing engineers. Book is dedicated to the memory of LaFrance and Peter Hatan. So we've got a contents page here. So chapter 1 is the basic concept, so radio waves, noise, sensitivity and selectivity, non-linearity in RF systems, digital modulation, spread spectrum systems, cellular radio, and radar systems. Chapter 2 is about frequency selective circuits and matching. So we've got series resonance circuits, parallel resonance circuits, inductive transformers, tune transformers, capacitive transformers, L network matching, pi and T networks, matching examples, component reality, and then chapter 3 is active devices and amplifiers. Chapter 4 is mixers, modulators and demodulators. Chapter 5 is about oscillators and phase-locked loops. Chapter 6 is about transmission lines and scattering matrices. Chapter 7 is about power amplifiers. Chapter 8, filters. Chapter 9, electromagnetic waves. Chapter 10, antennas. Chapter 11, propagation. And chapter 12, digital techniques in radio. So we've got a list of figures here as well. Give the preface a skip, and we'll just read a couple of pages of the basic concepts. So, chapter 1, basic concepts. Broadly speaking, radio frequency, or RF technology, or wireless as it is sometimes known, is the exploitation of electromagnetic wave phenomena in that part of the spectrum between 3 Hz and 300 gigahertz. It is arguably one of the most important technologies in modern society. The possibility of electromagnetic waves was first postulated by James Maxwell in 1864, and their existence was verified by Heinrich Hertz in 1887. By 1895, good luck pronouncing that, Macroni had demonstrated radio as an effective communications technology. With the development of the thermionic valve at the end of the 19th century, radio technology developed into a mass communication and entertainment medium. The first half of the 20th century saw developments such as radar and television, which further extended the scope of this technology. In the second half of the 20th century, major breakthroughs came with the development of semiconductor devices and integrated circuits. These advances made possible the extremely compact and portable communications devices that resulted in the mobile communications revolution. The size of the electronics continues to fall, and as a consequence, whole new areas have opened up. In particular, speed spectrum communications at gigahertz frequencies are increasingly used to replace cabling and other systems that provide local connectivity. The purpose of this text is to introduce the important ideas and techniques of radio technology. It is assumed that the reader has a basic grounding in electromagnetic theory and electronics. This text is not intended to be a comprehensive description of radio, but rather to provide the reader with sufficient knowledge to be able to appreciate the more advanced literature on the subject. The current chapter introduces some basic ideas concerning radio frequency systems, and subsequent chapters address various aspects of the technology. So chapter 1.1 is about radio waves. So for a static electric field resulting from a bounded system of charge, the field strength E will fall away at least as fast as the inverse square of the distance r from the source. And that's represented in this little formula here. If the system suddenly changes from one static configuration to another, the effect of this change will travel out from the system as a pulse. The pulse will travel with the speed of light, which is 3 times 10 to the 8 meters per second, and hence, after time t, will be at distance r equals ct from the source. Remarkably, the amplitude of the pulse will only fall away as r to the minus 1, and this means that at large distances, the effect of the pulse far outweighs that of the static fields with which it is associated. In principle, the system of charge can be modulated so that the fields carry away information as a series of suitably spaced pulses. As the pulses pass a second system of charge, the electric field will set these charges in motion and the pulses can be detected. The important point is that information can be carried over great distances due to the slow rate at which the pulse amplitudes decay. A dynamic electric field cannot exist in isolation, and the electromagnetic theory of Maxwell predicts that there will be a magnetic field pulse associated with the electric field pulse. In fact, the electric field E of the pulse will be related to the magnetic field H through this, so E is equal to some constant multiplied by the magnetic field, where this constant is the impedance of the free space. Furthermore, the electric field, magnetic field, and propagation direction will be mutually orthogonal. So as you can see in this diagram up here, means they're all orthogonal to each other. So that's what mutually orthogonal, they're all at right angles to each other. So the electric field's at a right angle to the magnetic field, and both are at a right angle to the propagation direction. Far from the system of charge, the energy is given by this formula here. So K of t is some function, depends upon the source modulation. So we've got K of t minus r over c, and then all of that is over 4 pi r. In general, any accelerating charge will give rise to a field that only falls away as r to the minus 1, and this leads to great variety of ways in which fields suitable for radio communication can be generated. In particular, charges can be made to oscillate at a particular frequency and this gives rise to a field for which functions KOT in particular, charges can be made to oscillate at a particular frequency omega, and this gives rise to a field in which the function KOT is of the form A cos of omega t plus phi. So A controls the amplitude of the field and phi its phase. The advantage of generating such a field is that it can allow many communication systems to coexist by operating them at different frequencies. Detection systems can be tuned to a particular frequency in order to receive signals from a particular source. In order to transmit information, the source will need to be modulated in some sense by this information. The modulating signal itself will occupy a range of frequencies known as the baseband, and this will have a bandwidth that depends on the data rate. Modulation will cause the transmitted signal to spread in frequency around the purely sinusoidal carrier, and, depending on the type of modulation, this spread can be wider than the bandwidth of the original baseband signal. Consequently, the type of modulation is an important consideration in allocating frequencies to users of the radio spectrum. Modulation is achieved by varying either A for amplitude modulation, AM, omega for frequency modulation, FM, or phi for phase modulation, PM. Alright, we're going to stop there for now. Do let me know if you find this book interesting and you would like me to continue to read through it. And if you have any other science, technology, engineering or maths related topics or books that you would like to see on this channel, then please let me know down in the comments.